Thank you. Vice-Chancellor, ladies and gentlemen, vision is hard. What a curious thing to say. What might I mean by that? It doesn't feel hard. We open our eyes and we see, instantly, effortlessly. But that only happens because our visual systems have evolved to do their job extraordinarily well. So well that most of the time we don't even notice what they're doing. Now let me try and illustrate at least part of the problem with this first slide. This is a light map of the back of the eye. Now the x and y dimensions then are simply x and y coordinates of the retina, and the z dimension is light intensity coming out of the page. Now, if any of my students are here, they will have seen this before, and my daughter as well. Shh. But the rest of you, can you hazard a guess as to what this person was looking at in order that this light map might be produced on the back of their eye? In other words, what was the visual stimulus that produced this? Any ideas? Can we work it out? Clouds. Nope. Me? No. Okay. Here, actually, I just heard somebody nearly get something. That was somebody said animal. But hey, I think this is rather more elaborate than we might have imagined. How many puppies have we got there? 1, 2, 3, 4, 5. And there are some paws in the middle there that I think need accounting for. So 6 puppies. Now let's go back to that light map. Now that we know what the stimulus was, can we see or discern the 6 puppies in there? No, not a chance. You can't. But your visual system can. It knows what it's doing. In other words, the point is that from all this mess, the starting point for vision, vision is able to extract meaning. So when I say that vision is hard, what I mean is it's a difficult information processing task. Our visual system does it very well. Our job as a vision scientist is to figure out how it is doing that. And that kind of leads on to the second way that vision is hard. How do we get in to see what's going on? In other words, how do we gaze in to see how we gaze out? Well, one thing we might do is gaze into the eye with an ophthalmoscope. And if we do, that's what we see. This has enormous clinical importance and value, of course, but it tells us absolutely nothing about visual perception. Another thing we might do is put people in brain scanners. We do quite a lot of this at Aston. And that's very good for lighting up parts of the brain depending on what the visual stimulation was. So that can tell us where, and it can tell us a little bit about what, but it tells us very little about how. What we really want is a link between visual stimulation out there and a behavioural or performance type response by the human being in order that we can figure out what's going on in between. This is the world of psychophysics. This is a typical psychophysics lab. We put our participants in the chair here. We usually call them observers, with their chin in the chin rest. We display things to them on the display screen there, and they respond in a prescribed way using the mouse, which seems to have gone AWOL in this photograph, but you get the general idea, indicating their response to those stimuli. So this is a typical stimulus that we use. It's a patch of sine wave grating. And we might, for example, want to know what's the lowest contrast that we can present that stimulus at, such that our observer can just about detect that it's there. So how are we going to do that? Well, this is one way. This is a widely used way. We're going to present a whole sequence of trials, and each trial consists of 2 stimulus intervals, each of which is indicated by an auditory beep. So it might go like this. Beep, beep. And the task is which interval contained the stimulus. Now that was a really easy one. It was the first interval, so we pressed the left mouse button. Now we do it again. Beep, beep. There it was in the second interval. Easy again. But the computer's going to present hundreds and hundreds and hundreds of these trials, and sometimes the contrast will be very, very low. Sometimes so low, it's still there on the screen, but it's below what we can detect. Now, if you can't see it, you're going to guess, and you're going to be correct 50% of the time. That means at the end of the experiment, we can plot percent correct as a function of stimulus contrast and generate what is known as a psychometric function. We can then figure out the contrast associated with the 75% correct point, and that's what we call contrast detection threshold. And in this example, that happens to be 1%. Now, this is an objective measure of human visual performance. So how does all that relate to what's going on in the brain? Well, vision begins in the eye. About 50 milliseconds later, the signal makes its way through to the primary visual cortex. It then starts to work back forward again through the temporal lobe, eventually getting up to the frontal lobe, where decisions are made, in this case, which button to press. The decision is passed on to the motor cortex, and that sends the signal down to the hand and the finger, and the response is made. Okay, contrast detection. This might not seem that exciting, but it turns out that from these humble beginnings, we can really make a lot of headway in figuring out how the visual system works. It's as though we're gazing into the deepest recesses of the system. We can only do that if we are effective with our stimulus design. Here's just a small selection of the stimuli we've designed in my lab over the years to give us the analytic power that we're looking for. Now, hand in glove with visual psychophysics comes computational modelling. So the idea is that we take a human being, we run him or her through a whole sequence of those psychophysical trials, we gather lots of data, we plot them. We then do exactly the same thing with an artificial observer. And the idea is that if the artificial observer behaves in exactly the same way as the human being, then, well, presumably, since we know how the artificial observer works because we've built it, then we've learnt something about the human being. Now, of course, we don't actually have to build Robbie the robot to do this. After all, our stimuli are held within the computer, so we don't need artificial eyes. And when we make a response with the mouse, well, that goes back to the computer, so we don't need artificial hands either. So actually, we can dispense with the robot and just replace it with a piece of computer code. Nonetheless, I'm going to use that little icon to remind us what this sort of computational modelling exercise is all about. Okay, I present this next slide with some trepidation. I don't think there's any controversy here. Consciousness does not live in the eyeball. The optic nerve is a one-way street. There's no feedback back down to the eye. Now, this is not going to be a lecture on consciousness, let me assure you of that. But I do want to say that I think that actually it's unlikely that we have real conscious access to what's going on in the back brain either. Now, that is rather controversial. Some people will take a different view. So let me qualify it by saying that if we can get the fingers of consciousness into the primary visual cortex V1, then we don't have open access to all of the machinery that we find there. In fact, higher level interpretive processors put some restrictions on what parts of that machinery we can read, and we'll see examples of that later. Okay, the Vice-Chancellor mentioned the canoeing. I have several other sort of colourful hobbies and, well, actually interests, the first three. I don't actually do any jousting myself. A hobby in the last one. They look wonderful in colour, but I'm afraid they're going to fade to grey. Far less delightful like that. But the fact of the matter is that in vision science, we make life so much easier for ourselves by working in black and white and dispensing with the colour. And that's pretty much what I've done for most of my career. I can see Dave smiling there because he went exactly the opposite way around. Having said all that, what I will do if I've got time at the end of the lecture is I'll try and inject a bit of colour back into proceedings. Okay, let me give you a brief overview then of the rest of the talk. We've had a fairly lengthy introduction, but the main meat of the talk is this green route, which is going to be sort of a bit of a walk through the psychophysical research that has taken place in my own laboratory, most of it here at Aston. But I'm going to punctuate that with a series of demonstrations, sort of breakouts, really just to provide some light relief and fun. But at least these things will sort of loosely relate back to some of the things I've already said and some of the things that I will come on to say. Loosely relate being the key phrase there. Okay, right, let's start off with a demo then. I want to talk to you about something called size constancy. I have two discs here. They are the same size, 10 centimeters across. And I'm going to give one of them to Marco here, and one of them to somebody at the back here. And I would like you to hold both of those discs up. It says A at the front, B at the back, so I can take a good look at them. Okay, now on the B at the back there's a question written on the back. Can you read that out for me? Which disc looks larger, A or B? Well, they both look the same. They do. Now, hold on a minute, you might say. That's okay, you can put them down. That's cheating, you might say. I know that they are exactly the same size. I've just handed them out. Well, yeah, fair enough. But we can imagine doing a meaningful experiment where we had discs over a range of sizes at both the front and the back, and I made lots of comparisons. And indeed, when people have done that kind of experiment and done it properly, it turns out that we're actually very accurate at making these judgments. In other words, objects that are physically the same size look to be the same size, even though they're at different distances. Now, hold on, you might say, well, what's the point of this? That's hardly surprising, is it? Well, it depends on what you think about the starting position. Let's have a look at what's going on the back of the eye, which I flipped upside down because, of course, everything is upside down. But let's not confuse ourselves. There's the A disc at the front. Above it in the retinal image is the B disc, which is just absolutely tiny. If you can't see it, it's there. They didn't look different sizes to me, and I'm quite sure if you were standing here, they wouldn't have looked different to you either. So what's going on? Well, certainly consciousness doesn't live in the eyeball. But what I was doing as I was standing here is I was using all sorts of depth cues, so linear perspective, texture gradients, stereopsis and so forth, to build up a depth map of the scene. And from that I deduced that the disc at the back was about 5 times further away from me than the disc close to. Therefore my system knows that in order to make size comparisons across the two discs, I have to either scale up the disc at the back by a factor of 5 or scale down the closer one by a factor of 5. You can go either way, it doesn't matter. This is what is known as size constancy. We're doing it all of the time. We don't notice that we're doing it, but it's a very important part of our visual perception. Okay, we'll come back to that in a moment. What I want you to do now is just gaze at that red dot. And we have to do this for a few seconds. This is what we call adaptation when we look at something for a long time. Gaze at that black dot, and in a short while I'll remove that and we'll be left with just a blank screen. But you should notice something rather interesting, depending on your definition of interesting, I suppose. Thank you very much. Okay, we're going to do that again, and while we're doing that, I'll explain what was going on there. But this time, when I remove Elvis, instead of looking at the screen up here, I want you to transfer your gaze down to that white card in front of you. And I could do with one of these myself. Is that a spare one? Yeah. Okay, so I want you to be looking at that red spot, building up the adaptation, and while you do that, I will explain what was going on. So look, while you are looking at the light regions, the receptors in the back of your eye that are seeing that, well, they get excited, but they also become fatigued. They become sort of worn out. Whereas the ones that are looking at the dark regions, well, they're undernourished. They're not responding at all. Then when you remove that stimulus, well, the undernourished ones are ready to go when they see the blank uniform white, but the fatigued ones are not so happy. They've slowed down a bit, and so you see a negative afterimage. Why was Elvis easier to recognise in the negative afterimage? Well, that's just simply the fact that our face recognition machinery is polarity sensitive. That's all there is to it. Okay, right, transfer your gaze to the card. You should see Elvis again, but this time he's tiny, and actually the effects will be even bigger for those at the back of the room. Of course he's tiny. I mean, Elvis now fits on this white card. He filled the entire screen before. So what's going on? Well, this is size constancy at work. When you're looking there, Elvis is a long way away. You scale up the size of the object associated with the retinal image. When you look close to, the size of the negative retinal afterimage is exactly the same as it was before, but because the object is now close to you, you scale down the perceived size of the object. So size constancy happens all of the time. We don't know we're doing it. It's just a free-running part of the system. Right, back to the grind. And we're going to do a bit of theory. Right, the receptors on the back of the eye, they're very good at measuring light intensities. So they're very good for giving us a high resolution representation of the image. But that's about all they're good for. You know, they're really just a bunch of isolated numbers. So they're just giving us that sort of light map of the puppies that we saw at the beginning. What we want to do is build up a description of the image, and in order to do that we need to know something about the spatial relations of the light levels on the back of the eye. And a sensible way to start with that is to measure what we call local luminance contrast. So here's an example stimulus, and the process I'm going to describe, really we should imagine this happening all the way around the boundaries of this stimulus, segmenting it from the white background, identifying what it is. But I'm just going to work on a little segment of this letter. So I'm going to get rid of the rest of the letter, rid of the rest of the text, put that up there, put it against a grey background. And now I'm going to add some numbers to this little patch of the stimulus. Relative to the grey, white gets +1, and relative to the grey, black gets -1. Now I'm going to build an analyzer. And a reasonable starting point might be to say, well, hey, we want to preserve what we find on the back of the retina and then do something with it in the rest of the brain. So that might seem a reasonable starting point. We multiply them together. 1 times 1 on the top is 1, -1 times 1 on the bottom is -1. And then perform linear summation within the analyzer, which gives us, as my daughter would say, a big fat nothing. Which isn't so good. So we don't like that. Something's gone wrong. Well, the stimulus is what the stimulus is. We can't change that. So let's have a different approach to the analyzer. Let's match the analyzer to the stimulus. Now we've got 1 times 1 on the top, and -1 times -1 gives us 1 on the bottom. This is looking more promising. Now we sum over the contents of the analyzer. 1 + 1 gives us 2. We've got an output. We've detected that contrast. That's looking pretty good. Now, look, I've started here with a high contrast sort of patch of stimulus. I needn't have done that. I could have started much lower, and that gives me somewhere to go. So let's suppose this is the stimulus that produces 2 on the output. I'm now going to double the contrast. So these numbers, each of them double. And look, if we work through the simple maths, the output has doubled as well. Let's double the input again, and the output doubles again. This is looking pretty good. If we plot a graph that shows analyzer response as a function of stimulus contrast, then we get a straight line. In other words, what we've done is built a linear contrast analyzer. And we might feel quite pleased with ourselves about that. This is the sort of device that might be useful to the visual system. There's something else that we can do. In fact, there are lots of other things that we can do, but just one thing that we've got time to talk about. We might square that output stage. Now, if we do that and work through a whole sequence of contrasts on the input, then we end up with a square law relationship between the stimulus in and the analyzer response out. So, we might now ask ourselves, given the sort of the value that we can see in these analyzers, is this what vision does? There are several elements here that we might want to know about. The general form and shape of this analyzer, sometimes we call that a receptive field. This linear summing operation over the contents of the analyzer. And this squaring operation here on the output of the analyzer. And let's think about that first. Now, remember the psychometric functions from before? Well, it turns out, if you work through the maths, and we're not going to do it, you'll be pleased to know, it turns out that what we call a shallow psychometric function is the signature of a linear analyzer. Whereas what we call a steep psychometric function, that's the signature of a square law analyzer. So actually this is looking quite good. We simply measure these psychometric functions, measure how steep they are, and that tells us which one of these analyzers we have. Unfortunately, there's a caveat. You see, it turns out that that first thing is true only if observer uncertainty is low. And I'll explain what I mean by that in a short moment. But if observer uncertainty is high, then even if the analyzer is linear, we can still end up with one of these steep psychometric functions, which causes us a problem, or it might do. You see, if we run the experiment and we get that result, we're home and dry. But if we run the experiment and get that result, there are two possible interpretations, which leads to a bit more head scratching. Okay, now what do I mean by this visual uncertainty? Well, it turns out there are 300 million cells just in V1 alone. So how does the decision maker know which cells it should be looking at in order to make the right decision? If it wastes its time looking at the wrong visual neurons, just picking up internal noise, that will cause performance to decline. Detection thresholds will go up, and as it turns out, the slope of the psychometric function will become steep. We're going to have to get to the bottom of this, but we'll leave that cliffhanger there for just a moment and have another demo. The white van illusion. Is it really an illusion, I wonder? A long, thin van and a short, fat van. Two different sized vans, therefore they must have different sized roofs. That follows, right? Okay. I'm going to rotate that red figure round, and I promise you I'm not going to change its size or its shape. This worked much better in the old days when we had overhead projectors. You could see I wasn't cheating. Perfect match. In other words, those two roofs, even though they look completely different, are identical. So what's going on here? Well, it's size constancy doing its thing again. This van recedes in depth that way, so we scale up the far end of it. We scale up the length. This van recedes in depth across its width, so we scale up in that dimension, making it nice and fat. The point is that primary visual cortex contains the precise machinery that we need in order to make the measurements of the roof size on the back of the retina. But this kind of demonstration clearly shows that, well, we're not able to consciously access that machinery and get it to work, because no matter how we look at those roofs, they do not look to be the same size. Right, here's another one. I think everybody here sees a grey tab on top of a white tab. But let's just mask off some of the image. I think we're there. The paint is exactly the same in both tabs. Now, again, people are often surprised by this. You could hear sort of the gasps of amazement in the lecture room. But why should we be surprised? Why do we want vision to be able to read off the raw luminance values? Vision doesn't and shouldn't care about those values. What vision cares about is the reflectance properties of the objects out there in the real world. And in this case, the visual system has very carefully deduced that that is grey on the top and white on the bottom, because it's taken account of lighting from above and the shadow beneath it. So we see the stimulus correctly. So once again, we see that we're not able to access the sort of primitive basic measurements that we might expect primary visual cortex to make, but rather a higher level representation of the stimulus. Okay, back to the grind. We were grappling with this sort of square law and uncertainty. Well, we're going to start by measuring the psychometric function. Now, plenty of people have done this before, but I think never before with the precision that we did it, and also over the number of stimuli that we did this for. These are the results for two observers for the different rows. That's the prediction for the shallow psychometric function. That's the prediction for the steep psychometric function. You couldn't ask for a clearer result. Clearly, red wins. But now we do have a problem, because remember, we can program Robbie the robot in two different ways for him to behave so that he gives us that red prediction. He might be a square law type observer with low uncertainty, or he might be a linear type observer with high uncertainty. He would behave in exactly the same way. So how are we going to get to the bottom of this? Well, the thing we need to do is manipulate uncertainty experimentally. And we're going to do that by varying stimulus size. In fact, we have 6 different sizes. There they are. We're going to measure detection thresholds for those. But the cunning thing here is in the experimental design. In what we call interleaved design, we randomise the choice of stimulus every trial. So the observer doesn't know what the size of the stimulus is that they're trying to detect from trial to trial. They are uncertain about the stimulus. In the blocked design, we run a whole sequence of trials that are exactly the same size, so the observer knows what they're looking for. So we haven't imposed any uncertainty on them. In this experiment, we're not interested in the slope of the psychometric function, but the contrast detection thresholds, which, as I mentioned before, are also affected by uncertainty. And these are the results. So the first thing to notice is that performance improves as the stimulus grows from small to large, so low thresholds here, higher thresholds there. But the headline result is the gap between the black and the red function. Look, the stimuli were the same in both of those conditions. The only difference was the uncertainty that we inflicted on our observer with our design. And the uncertain observer is worse than the less uncertain observer. Now, this is a really important result, because it turns out that when you work through the maths for the fairly modest levels of uncertainty that we introduced through our experimental procedure, for that to show up in the experimental results, it follows that the internal uncertainty within the observer must be very low. If it was high, thousands or millions, it would swamp the experimental results that we've seen. In fact, our sort of formal analysis on 2 other data sets, in fact, lead us to believe that the internal uncertainty is really very low, about a factor of 3, which is much, much better than the factor of thousands or millions that it could have been in principle. Now, it also follows then that if internal uncertainty is very low, that steep psychometric function must owe to a square law on the output of the analyzer. Okay, so we've got square law contrast transduction, but why do we do that? Why would the visual system take the square instead of sticking with something linear? Well, as any signal processing engineer would know, what we've got here is something, well, essentially it is an energy detector. And it turns out that that is exactly the right sort of thing to do if you don't have precise knowledge about the form of the waveform that you're trying to detect. And in general, this is going to be true for the visual system. For example, just small eye movements mean that from trial to trial, we're not going to know exactly where the peaks and troughs of the waveform are on the back of the eye. So it turns out that the visual system has evolved to use a strategy that is the correct one to use. It follows sound engineering principles. We also know, if we're a signal engineer, that if you want to detect energy, then you should be summing over the entire signal. In the case of our vision experiments, this means summing over the whole area of the stimulus. So is that what people do? So we brought in Robbie and we programmed him up to do exactly that. We put a few other features in there that we know the visual system has. And we ran him through the experiment, and look, here's the curves compared to the data points, which are the human observer. Very, very similar. The bottom line is, yes, we sum energy over space. How does this relate to what's going on in the brain? Well, we think energy detection sort of happens in the back brain. The local analysis happens, we think, in V1. And that global analysis quite possibly happens in V4. How to think about uncertainty? Well, in the main, the visual system is very good at picking the right neurons to make the decisions about. But perhaps also what it's doing is picking sort of the nearest neighbours as well, which are not so valuable, and that's adding to a little bit of uncertainty. Right, time for another demo. I'm going to now split you into two groups. Here is the dividing line. So all of you are Group A, and all of you are Group B. If you're not sure which side you're on of that dividing line, it doesn't matter, just pick a group and stick with it. Okay, now I'm going to show all of you, well, I'm going to show 3 images, but each and every one of you will see just 2 of them. So Group A, you will see the first image, Group B, you won't. Group B, you will see the second image, you lot won't, and then all of us are going to see the third image. Now, this is only going to work if you follow my instructions carefully. So no peeping when you're supposed to have your eyes closed. So let's begin with everybody closing their eyes. This is where I do a sharp X. Okay, everybody close your eyes. Keep them closed. Now, Group A only, open your eyes. Take a look at that image and close your eyes again, please. So everybody's closed now. Group B, open your eyes, take a look at that image and close them again. Okay, so everybody's eyes are closed now. Okay, everybody, open your eyes, look at that image, close your eyes again. Everybody's eyes closed. Right, okay, everybody, open your eyes. Right, you all saw 2 images. I'm going to ask all of you about the second image that you saw, so the one that we all saw together. Who saw an elephant? Good, nobody hallucinating. It's always worth checking that. Who saw a rat, or maybe a mouse? All right, so lots of people over here, hardly anybody over there. Okay, hands down. Who saw a man? Huh. Everybody over here, just 1 or 2 people over there. So this lot saw a man, this lot saw a mouse. We were talking about the second stimulus, right? The one that we all saw together. We do know the difference between a rat and a man. I'm sure we do. So what's going on? Well, I think it's obvious we need to see the whole sequence of images. This is the first image that I showed to Group A. It's a rat. This is the first image that I showed to Group B. It's a man. You all saw this. This is a rat man. Now, you were all looking at exactly the same stimulus, but your visual perception of that stimulus depended on how I'd primed you with the previous stimulus. But look, it's not just the fact that the stimulus is the same on the back of the eye. These kind of analyzers that we've been talking about, all the stuff going on in primary visual cortex, kind of crawling around this contour there, that's doing exactly the same thing for all of you as well. In other words, this kind of entire data-driven or bottom-up pathway that we've been talking about, that's doing the same job for all of you. The point that we've learned is that visual perception doesn't depend just on this bottom-up data-driven pathway, but influences from the top-down knowledge-based pathway also govern how we see. Right, back to the psychophysics. We were grappling with analyzers, weren't we? Right, it seems as though we might have done quite a lot. We figured out that we've got a square law there. We also figured out that there's something kind of missing from this diagram because we add things up over area, over space. But there are other things, other details there that we might still want to get to the bottom of. let me introduce you to our Battenberg experiment. Now, I don't have the time to go into the rationale behind designing this stimulus, but it turned out to be extraordinarily important in making headway with our understanding. Americans never get this, by the way. It only really works in the UK. So we measured contrast detection thresholds for all of these Battenberg stimuli. There's a huge amount I could say about this figure. I'll just try and keep it simple. Those, oh dear, they're not rendered very well here, are they? Those stimuli on the far right correspond with those thresholds. We wheeled in Robbie. We got him to behave like an energy detector as before. That gave us the black curve. He did extraordinarily well. So this confirms what we knew before. That green curve is the prediction by people's ideas that have dominated the literature since the 1980s. I don't have time to describe it, but it's wrong anyway. What I want to concentrate on is the data points for this stimulus and this stimulus. And although you can't see it in this slide, the number of elements in that first stimulus is twice as many as in that second stimulus. Also, sensitivity for that first stimulus is twice that for the second stimulus. In other words, we need half the contrast to detect this thing as we do to detect that thing. So when you think about it, at contrast detection threshold, if we sum the contrast over the entire stimulus, then we get the same numbers for both of those stimuli. So in fact, I think that's sort of good evidence for this linear summation operator within our analyzer. But we can actually say rather more than that. We want to know about the shape of this analyzer, the receptive field. So we wheeled in Robbie and we said, look, you know, try a whole series of different analyzer shapes and tell us what works best. So Robbie did that, and this is the answer that he came up with. The receptive field is much larger than the toy receptive field that we've been thinking about so far. And I think you can see why this is what emerged from that Battenberg experiment, because look, if we place a couple of Battenberg elements side by side, they fit exactly within that receptive field. So we get this perfect linear summation within that analyzer. And that's why the stimulus on the left is twice as easy to detect as the stimulus on the right. Receptive fields of this type are sometimes referred to as filter elements because they're selective for orientation, for size, and various other image features. Okay, visual textures are ubiquitous in the visual world, and we really think that this is what the energy detection is all about. For example, can you see that sort of over in this corner here, the orientation of the textures can help us segment the mother from one of her puppies. Now, another thing that we know about texture perception in humans is that we can discriminate texture density. And we were kind of interested in this. So we measured detection thresholds for various texture stimuli, varying their size as we have done before, but also varying the texture density. We wheeled in Robbie and we programmed him up in many different ways, testing lots of different ideas. And the inescapable fact was that we could only get him to work if we built in mechanisms that had templates of the texture densities that we were trying to detect. In other words, our contrast detection experiment, this approach, has revealed the texture mechanisms that we think are used by humans in making texture discriminations. Okay, one more demo. This is called McKay's rays. I want you all to gaze at the center of this stimulus. We'll do this for a few seconds as before. And as before, after a little while, I will remove this stimulus. You'll be just left with a blank screen, but I want you to sort of take note of what you see. You might notice that some of those rays are starting to sort of drift around a little bit. You might even be seeing some colours. Actually, the longer we look, the more intense those colours become. They're not the points of this. I mean, they're quite interesting, but that's not what I'm going to talk about. Right, that's probably enough. This time you are hallucinating. You're seeing stuff that just isn't there. That's a completely blank screen. But I think you're probably all seeing this sort of swirling pattern, almost like grains of rice spiralling around. Unlike the negative retinal after image before, this after effect has no relation at all to that adapter. It doesn't look in any sense like the adapter. So what's going on? Well, we've been learning about the pattern module in the visual system, which we think is probably located in V4. There's also a motion module. I haven't said anything about that, and that's located in an area known as MT. Now, inhibition is ubiquitous in the brain. It's a good idea. It keeps everything clamped down. It stops visual neurons running away with excitation. So we think that this motion and pattern module actually strongly inhibit each other, even without any activation within those modules. So what happens is when we look at McKay's rays, we adapt this pattern module, we fatigue it, it becomes less responsive. So then when we remove the adapting pattern, this inhibitory influence is also removed. The motion module becomes disinhibited and bursts into life. And of course, normally, when that motion module is activated, that's because there is motion across the retina. And so that's what we see in this situation. Activity here signals motion, and we see it, even though there is no motion on the retina at all. Okay, back to the psychophysics. We've spent most of our time talking about detection thresholds. Perhaps it's now time to move things up above detection threshold to stimuli that we can clearly see. So let's turn on the telly, see what's on. As zebras escaped from the zoo. This is what we might call a high contrast image. Indeed, parts of the image are locally very high contrast. Zebras are psychophysicists' favourite creatures. There are other regions in this image that are actually of much lower contrast though. Right, let's take the TV remote and turn down the contrast of the TV. So this is now what we might call a low contrast image. But it still contains local regions of contrast that are actually higher than the low contrast region from the previous image, which looked like that. In other words, what I'm saying is we can make judgments of the global contrast of a TV image or any other image, but just looking at the local measures is not sufficient. We need to perform some kind of global aggregation over the image. So how might we do that? Well, going back to contrast detection threshold, that equation at the top there, it's kind of the bare bones of the energy detector. We're simply summing up the squares of the local contrasts. Above threshold, though, we know that the situation is rather different. This second equation derives from some experiments I've done on contrast discrimination, which I don't have time to talk about. But from those studies, we know that the numerator, well, that stays the same as what we already know, but now we've got this second term that divides into that energy term. The local contrasts are just raised to a slightly lower exponent. And essentially, this is inhibition taking place within a single module, within the pattern module. And this inhibition is absolutely crucial to perception, because if you think about it, if it wasn't for that inhibitory term, then as we grow the size of a stimulus, it should look more contrasty, because that first equation, its value will go up. Now that's nuts. We don't want things to look more contrasty just because they've got bigger, and they don't. And the reason they don't is because of this contrast gain control property. That particular equation derives from Meese and Summers 2007, and so for that reason we sometimes refer to it as M and S contrast. Right, on to our contrast perception experiment. We're back to the Battenbergs again. What we got observers to do was adjust the contrast of this stimulus until it matched the global contrast of this stimulus. So we adjusted that one to match that one. This second one contains two contrast components. One of them was always fixed at 8%. The other took on values that varied from left to right across that graph. So what happened? Well, when that second component contrast was very low, perception was dominated by the fixed 8%. But then look, something really odd happened. As we continued to increase the contrast of this second component, perceived global contrast actually declined. This is like having a dimmer switch. You turn it up, the current goes up, but the lights come down before then going back up again, because thankfully sanity does return, and as the contrast gets higher and higher and higher, then that second component ends up dominating perception. But this paradoxical effect is really quite surprising. It's unusual. I'm not going to try and explain it. That would take too long. But what I will say now, because the next couple of slides are a little bit cluttered, the only model of contrast perception that we've been able to find that predicts this paradoxical effect is our own one. So that's kind of rather gratifying, really, that our understanding of contrast that emerged from a completely different set of experiments sort of had this emergent property that predicted this paradoxical feature. Okay, so we did the experiment on a whole sequence of Battenberg stimuli. We programmed up Robbie to test several different ideas about contrast perception, and the bottom line is they're all wrong apart from the pink one, including the yellow one, which is what's known as RMS contrast, and this is something widely used by image processing engineers. They've got it wrong. As Dan Baker said to me, one of my former students, this isn't just contrast. You could see the joke coming. This is M&S contrast. But this is what I think is the really exciting result here. That pink curve, we only get that pink curve if we exclude the filter elements that we already know about and operate on an element-by-element basis. That's a bit puzzling, isn't it? If we put those filters in, as we believe they should be, then in fact the pink curve becomes much more like this blue one. And we understand why. It's down to the linear summation within the receptive field. Wow, okay, so what's going on? You know, here's primary visual cortex. It's jam-packed full of these analyzers which are selected for different orientations, different spatial frequencies and so forth. You can't bypass them. There's no way of getting up to perception without going through these guys. So where have they gone in our experiment? Well, it turns out that if you have an appropriate set of filters like this, then mathematics performed by other people tells us that if you appropriately weight the right set of filters, including negative weights, then you can construct any type of filter element matched to any type of stimulus element that you might be able to conceive of. This is known as matched filtering. And if you think about it, it's kind of what we want, really, because when we look at a Battenberg element, and we can clearly see it, we want it to look like that. And that's perhaps what a matched filter would tell us about that. We don't want it to look like that, and indeed it doesn't. So what we think is going on here is that at contrast detection threshold, where there's very little evidence about the precise details of the stimulus we're trying to detect, the system does the smartest thing possible, which is it employs an energy detection strategy using the best filter that it can find. But once we've got good evidence of what the stimulus is, then it employs a matched filter strategy, delivering the best possible representation of the stimulus. Now, it's still early days with this. I think we've still got a long way to go, but I think this is an exciting direction in which the research is heading. Okay, I can see I'm running out of time, so I want to get this slide in. To extend my thanks to colleagues and mentors all of over the years. All of these people are responsible for helping me get to where I am now, certainly in the early part of my career. And thanks also to my students and postdocs who've implemented my ideas, tested them, taken them further, developed them, and had ideas of their own as well, of course. Let me say this, and the Vice-Chancellor sort of already said a few words along these lines. I think when most of us kind of gaze out to the stars at night, we do so with a sense of wonder. And I think psychophysicists have exactly that same feeling when they gaze into the dark, hidden corners of the visual system. Cosmologists make a career out of gazing into the sky, and like cosmologists, we're able to make observations. Like cosmologists, we are able to analyze data. And like cosmologists, we are able to develop theories. But unlike cosmologists, we are able to design experiments to test those ideas. Okay, I can see I've just about got enough time to do this because I'd said I wanted to try and inject a bit of colour back into proceedings. This is some work I did a few years ago now with Cathy Mullen in Montreal. She knows a lot about colour vision. I don't, or at least I didn't. Well, I still don't really. I do know how to program Robbie though. So we did some experiments using these coloured stimuli. I'm not going to go into the details. And we programmed Robbie up to tell us what types of analyzers were being used to detect these stimuli. And these were amongst the analyzers that emerged. And it turns out that these are perfect for performing actually not colour contrast assessments, as might at first appear, but these are really very good for measuring uniform regions of colour. We call them colouring in cells. And so I think the idea is that the mechanisms that we've been looking at for most of this lecture, they tell us about the contours of objects, the shading of objects, the texture of objects and so forth. But then after that's been done, these colouring in cells kind of fill in the rest of the stuff to give us a full, colourful visual perception. Back to those black and white interests, I'm going to inject some fake colour in there now. It's rather psychedelic, isn't it? What I want you to do is gaze at that central red spot, and we'll do this for a few seconds as before, and then we'll revert to the black and white image, but you should see something different. That's probably long enough. For a few moments there, the true colours of those images were reinstated. I'll leave it to all of you to think about what might have been going on in your brains in order for that to happen. Thank you.